Hello and welcome to this class of complex variables. Again, a very important topic to discuss. And let's start the topic. Now, first of all, we are going to discuss what is an analytic function. So for this, let us consider W. Let us consider W, which is a function of a complex variable Z, such that Z can be written as some real variable x plus jy. Here x and y are real quantities. So W is actually written as function of z, where z equals to x plus jy. So W is a complex quantity and it can be expressed as W as a function of z, which can be written as some constant u, which is a function of xy plus j v, and that is also a function of xy. Here both u and v are real functions and their variables are x and y. So W is a function of the complex variable z, such that z can be written as x plus jy. That is, W is a function of z. Then W is a complex quantity and it can be expressed as W equals to f of z, and that equals to u function xy plus jv, which is also a function of x and y, where both u and v are functions of real variables x and y. Now, W may be a single valued or it can be a multi-valued function. If we differentiate W with respect to Z, that is, if we find out W prime, that is f prime Z, which may be a single valued or it may be a multi-valued function. If W prime is a multi-valued function, then the complex quantity W is called a multiform function. If W prime equals to f prime Z is a multi-valued function, then W is known as a multiform function. It is a multiform function, then W can be regarded as a multiform function, as because W prime, that is the dw dz or f prime z, has multi values. Otherwise, if W prime is a unique valued function, then W is regarded as a analytic function. So here comes the term analytic function. So for W to be an analytic function, W prime, that is dw dz, must have a unique value. Otherwise, or in other words, we can explain it as if dw dz, that is W prime, has unique value, then only W can be regarded as a analytic function. Okay, now let's discuss about some properties of an analytic function, or rather conditions of analyticity of a function of complex variable. So now let us discuss about the conditions that must be fulfilled by a function to be an analytic function or to be an analytic one. Let W, that is f of z, it is function of xy, that is uxy plus j vxy. So del w will be del u plus j del v. So del w must be equals to del u plus j del v, and delta z, that must be delta x plus j delta y. Also delta u. Now delta u can be written as del u del x into delta x plus del u del y into delta y, and delta v also it can be written as del v del x dot delta x plus del v del y dot delta y. So delta w can be written as delta u plus j delta v, delta z can be written as delta x plus j delta y, and then I have written delta u as del u del x dot delta x plus del u del y dot delta y, and delta v equals to del v del x delta x plus del v del y dot delta y. So let us find the value of w prime. W prime means dw dz. Now it can be written as limit delta z tends to 0 dw, sorry, it is dw dz. So limit delta z tends to 0 delta w by delta z. Okay. Now that can be written as limit delta x tends to 0, delta y tends to 0, and delta w means that is delta u plus j delta v, and delta z again means delta x plus j of delta y. So now proceeding in the next step, we can write limit delta x tends to 0, delta y tends to 0, and then delta u. So we are substituting the value of delta u from this equation, that is delta u delta x dot delta x plus delta u del y dot delta y plus j, and then putting the value of del v, that is del v del x dot delta x plus del v del y dot delta y, and in the denominator part again putting the values of delta x plus j delta y as it is. So delta x plus j delta y. Now so we can write as limit delta x tends to 0, delta y tends to 0, and then del u del x, we can take delta x common and write it as del u del x plus j j del v del x, del u del x plus j del v del x dot delta x plus, again taking j common, we can write it as no, then we have to write delta y, taking delta y common, so it will be del u del y, it will be del u del y plus j del v del y dot delta y, and keeping the denominator term as it is, delta x plus j delta y. Now dividing both the numerator and denominator by delta x. Now dividing both the numerator and denominator by delta x and putting the value of the limit delta x tends to 0, what we get, that is limit, or as we are going to put the value of the limit, so w prime del x, del u del x plus j del v del x, as because dividing by delta x it will be 1 plus del u del y plus j del v del y, and dividing delta y by delta x, and then putting the value of limit delta x tends to 0. From calculus we can write it as dy dx, as because dy dx is equals to limit delta x tends to 0 delta y by delta x, so it will be dy dx, and then the denominator part, delta x divided by delta x becomes 1 plus j, and again delta y by delta x, putting limit delta x tends to 0, it will give us dy dx. So this will be the value. Now this can be written as this is equation 1, and we can write it as a, some constant a plus b m divided by 1 plus jm. So this is equation 2. Now what is the value of a and b? As from here we can write a as a equals to del u del x plus a equals to del u del x plus j del v del x. Let it be equation 3. B equals to del u del y plus j del v del y. Let it be equation 4. And m equals to dy dx, and let it be equation 5. So these are the constants a, b, and m. Okay. Now, as we are talking about analytic functions, just now I have explained that w to be an analytic function, this w prime must be a single valued function. So dw dz must be independent of m, or we can write that dw dm must be equals to 0. So dw prime dm must be equals to 0. So w to be an analytic function, w prime to be an analytic function, what we can write, that dw prime dm must be equals to 0. dw prime dm must be equals to 0. Now as w prime equals to this, so dw prime dm, ddm of w prime, that is a plus bm by 1 plus jm, must be equals to 0, or we have 1 plus jm whole square, then writing 1 plus jm. Now then differentiate of a plus bm, it will give us B minus A plus Bm, keeping A plus Bm, and then differentiating 1 plus Jm with respect to m, we will get only J, and that will be equals to 0. So we have 1 plus Jm B equals to J A plus Bm, and from both the sides we can cancel out JMB, so we left with B equals to JA. So we left with B equals to JA, and let it be equation 6. Now putting the values of B and A, that is from equation 3 and 4 in equation 6, we get, putting the values of A and B from equations 3 and 4 in equation 6, we get del U del Y plus J del V del Y, that is the value of B, equals to J into A means del U del X plus J del V del X. So here I am putting the values of A and B right from equations 3 and 4, and it will give me J del U del X minus, that is J square minus of del V del X. Now then I can equate the real and the imaginary parts from both the sides, and by equating the imaginary parts, what we get del U del X. Equating the imaginary parts, I get del U del X equals to del V del Y. So this is equation 7. By equating the imaginary part, I get del U del X equals to del V del Y, and then equating the real part, I get del U del Y equals to minus of del V del X. Del U del Y equals to minus of del V del X. So this is equation 8. So these are the two equations, or these are the two conditions that the complex function W must be analytic. So by holding these conditions, or if W holds these two conditions that is given in equations 7 and equation 8, then only the function W can be regarded as an analytic function. And these equations 7 and 8 are known as the Cauchy Riemann equations. So these equations 7 and 8, that is del U del X equals to del V del Y, it is one of the equations, and the other is del U del Y equals to minus of del V del X, and these two equations are the Cauchy Riemann equations. Okay, if you have any doubt, please comment here. Or is it okay? Is it okay for you? Ankita Shingo, no sir. No sir means, have you any doubt, Ankita? Ankita, have you any doubt? All clear, okay, Shilpa. No, sir, carry on. Okay. No, sir, all clear. Okay. Okay, fine. So let's move on to our next topic. So let's move on to our next topic, that is derivative of analytic functions. So let's find out the derivative of any analytic function. Again, for this, W is considered as a function of Z, and which can be written as uxy plus jvxy. Now, as from equation 1, just now we have derived equation 1, and from equation 1 we can write that is W prime, that is dw dz as del u del x plus j del v del x plus del u del y plus j del v del y into dy dx whole divided by 1 plus j dy dx. So here I have used equation 1 again. Since W is analytic, as W is analytic, it satisfies the Cauchy Riemann equations, and hence from equations 7 and 8, dw dz can be written as, so using equation 7 and 8, that is del u del x plus j del v del x plus, now then del u del y from equation 7, or from equation 8 rather, del u del y is equals to minus of del v del x. So putting the value of del u del y as minus of del v del x plus j del v del y means del u del x into dy dx, and keeping the denominator same, that is 1 plus j dy dx. So we have del u del x, taking del u del x common from the numerator, we get 1 plus j dy dx plus j del v del x common, j del v del x. So here also 1, and j del v del x, as I am taking j del v del x as common, so let it be 1 plus j and then dy dx, as because j square means minus, and it will give this value, that is minus of del v del x, and whole divided by 1 plus j dy dx. So it can be written as del u del x plus j del v del x, del u del x, del u del x plus j del v del x, or it can be written as del del x of u plus jv, and as because u plus jv means z, so it can be written as del z del x, and let it be equation 9. So this is the value of dw dz using the Cauchy Riemann equations. Now, also by using equations 7 and 8, I can write, so I'm omitting this part. Also by equation 7, 8, we get dw dz equals to del u del x plus j del v del x. Del u del x means from Cauchy Riemann equation, it means del v del y minus j del u del x. So it can be written as minus of j square. J square means minus 1. So it can be written as minus j square del v del y minus j of del u del x. Taking minus of j common, it can be written as del u del x. Here I can put del u del x as del v del x means del u del y. Sorry, it will be del u del y. So taking minus j common, it will be del u del y plus j into del v del y. So it can be written as del u del y plus j del v del y, or minus of j, I can write it as 1 by j del u del y plus j del v del y, or it can be written as del y. So 1 by j del y of u plus jv, or it can be written as 1 by j into del z del y, and let it be equation 10. So either in the form of equation 9 or in the form of equation 10, dw dz or derivative of a complex variable can be found out, and these equations 9 and 10 give the simplified expressions for the derivative of w. So this is how derivative of an analytic function can be found. Is it okay? Again, I am asking for your comments. Is it okay? Then I will proceed to discuss some properties of analytic functions. Okay, thank you, Shilpa, Satyajit, Orpita, Ujjal. So let's move on to discuss some properties of analytic functions. Properties of analytic functions. This is the next topic to discuss, that is properties of analytic functions. Now, number one, the first property is both real and imaginary parts, both real and imaginary parts of analytic function satisfy Laplace's equation in two dimensions. Laplace's equations, that is del 2 phi del x2 plus del 2 phi del y2 plus del 2 phi del z2 equals to 0. As you know, this is the Laplace's equation in 3 dimensions, but a property of analytic function tells us that both real and imaginary parts of analytic function, as the real part is our x and the imaginary part is our y. So both real and imaginary parts of an analytic function must satisfy Laplace's equation in two variables, that is del 2 phi del x2 plus del 2 phi del y2 equals to 0. Now let's prove this property. That is, the property is del 2 phi del x2 plus del 2 phi del y2 equals to 0. This is the Laplace's equation, and the real and imaginary part of any analytic function must satisfy this Laplace's equation. To prove this, let's start with equation 7 and equations 8, that is the Cauchy Riemann equations. In equation 7, we have del u del x equals to del v del y. We have del u del x equals to del v del y, and in equation 8 we have del u del y equals to minus of del v del x. It was our equation 7 and 8. Now differentiating both equation 7 and 8 with respect to x and y, and we will have del 2u del x2, that will be equals to del 2v del x del y. This is from differentiating equation 7 with respect to x, and by differentiating equation 8 with respect to y, we will del 2u del y2, that must be equals to minus del 2v del y del x. Okay, now here we have admitted that the orders of differentials are interchangeable, that is del del x or del y can be interchanged, and addition of these two, that is if we added up del 2u del x2 plus del 2u del y2, as because we are going to prove the Laplace's equation, so we have to add del 2u del x2 plus del 2u del y2, and it will have del 2v del x del y minus of del 2v del x del y, as because we admitted that these differentials are interchangeable, so it becomes 0. This is the first property of analytic function, and the property says that the real and the imaginary part of any analytic function must satisfy Laplace's equation in two dimensions, that is, it must satisfy del 2u del x2 plus del 2u del y2 equals to 0. So the first theorem or the first property is proved. Now let's move on to the next property or the second property. Now here something to be noted. Okay, now the functions that satisfy Laplace's equation, are called harmonic functions. So the functions that satisfy Laplace's equations are known as harmonic functions. Hence here in this property or in this problem, u, that is function of xy, and v, again a function of xy, they are harmonic functions, as because these u and v satisfy this equation, that is they satisfy the Laplace's equation, and if any function satisfy Laplace's equation, they are known to be harmonic functions. Two functions satisfy Laplace's equation and the Cauchy Riemann equations are called conjugate harmonic functions. Just remember this term, that is conjugate harmonic functions. So two functions that satisfy both Laplace's equation as well as Cauchy Riemann equation, they are called the conjugate harmonic functions. Okay, so let's move on to the second property. Property number 2 tells us that the analytic function W, is a function of Z alone. The analytic function W is a function of Z alone, and it is independent of the complex conjugate Z prime or Z bar. The analytic function W is a function of Z alone, and it is independent of the complex conjugate Z prime. Okay? Very hot and humid today. Okay. Again, to prove this, let us consider W as U of xy plus J V of xy. Z equals to, as we know, this is x plus jy, then Z prime, it will be x minus of jy. Now dw dz means that is del z of u plus jv, and it will be del u del z plus j del v del z. Or let us find out dw dz prime. So it will be del z prime, and it will be del u del z prime and plus j del v del z prime. Then del u del z prime can be written as del u del x into del x del z prime plus del u del y dot del y del z prime. This is del u del z prime plus j, and then writing del v del z prime as del v del x dot del x del z prime plus del v del y dot del y del z prime. Now, as from these two equations, that is, if z equals to x plus jy and if z bar equals to x minus jy, then we can write x equals to, adding these two equations, we get twice x equals to z plus z prime. That means x equals to z plus z prime by 2. And subtracting these two equations, we get twice jy equals to z minus z prime. That means y equals to z minus z prime by twice j. So here from these two equations, we calculate the value of x and y. Now from this x, the expression of x, del x del z, del x del z bar, del x del z bar should be half, as because half of z plus z prime, so the value will be half, and del y del z prime becomes minus of 1 by 2j. Now multiplying j in both the numerator and denominator, we get that is j squared, that is minus a plus, and it will be only j by 2. So del x del z bar and del y del z bar, we have calculated the values of del x del z bar and del y del z bar, and then we are going to put these values in the above equation. So we have del w, or we have del w del z bar, del w del z bar So we are going to put these values here, that is dw dz bar. It will be del u del x, then del x del z bar. So putting the value of del x del z bar, that is half. So it will be half of del u del x, then del u del y into del y del z bar, that is j by 2. So it will be plus j by 2 del u del y. Then the second part, that is plus j plus j, then del v del x dot del x del z bar. So again putting the value of del x del z part, that is half that is half del v del x, and then again putting the value of del y del z bar as j by 2, that is plus j by 2 into del v del y. So after substituting the values of del x del z bar and del y del z bar in the expression of dw dz bar, we obtain this. Then I can take half common. So by taking half as common, we have del u del x minus del v, that is j, and j means j square. So that is minus del v del y. These are the real terms, and then j, taking j common, that is del u del y plus j common, so that it will be del u del y plus del v del x. Okay. Now again we are going to apply those Cauchy Riemann equations, that is del u del x equals to del v del y and del u del y equals to minus of del v del x. So again these two equations are to be applied here, and we get dw dz bar. dw dz bar equals to half del u del x means del v del y. So del v del y minus of del v del y, then plus j. Del u del y means again minus of del v del x, and the last term was del v del x itself. So we have found that all the terms cancel with each other, and we have dw dz bar equals to 0. Hence, we can prove that the analytic function w is a function of z alone, and it is independent of the complex conjugate z prime, as because dw dz prime here equals to 0. Any doubt? Any query or any doubt from up to this part? Yes, Satyajit, that's right. That whenever a function is an analytic one, it must satisfy the Laplace's equation in 2 dimensions. So it must be a harmonic function. Yes, that's right. Actually, since this is a online class, so I can't get you all. So every time I'm asking for your feedback or your comments, and from your comments only I can get you that whether you are getting me or not. Okay, Ankita, Kaushik, okay, Amit, Satyajit, fine. So let's move on to the third property. Let's move on to the third property of this analytic function. So we have already stated and proved two properties of analytic functions. Now the third property. Okay, Shikha, fine, fine. So let's move on to the third property, and this property tells that in any analytic function W, which is actually u function xy plus j function or v xy, the family of curves given by uxy equals to k1 and vxy equals to k2 are orthogonal to each other. Again, I am stating this property that in any analytic function w equals to u xy function xy plus j v function xy, the family of curves given by u of xy equals to k1 and v of xy equals to k2 are orthogonal to each other. That means the slope of this family of curves, we have to prove we have to prove that the slope of this family of curves, that is m1 and m2, if we find the products of m1 and m2, that is the slope of this family of curves, they will give me minus of 1. And if it is true, then if we can find out that m1 and m2 equals to minus of 1, that means we can prove this statement. So the slopes of the family of curves uxy equals to k1 and vxy equals to k2. So the slopes are, if m1 is the slope, that is dy dx, that equals to minus of del u del x by del u del y, and m2, if m2 is the slope of the family of curves vxy equals to k2, then m2 equals to dy dx, it is also given as minus of del v del x by del v del y. Now just multiply these two, that is product of m1 and m2. Now since u and v are the components of the analytic function, they must satisfy the Cauchy Riemann equation. So to find out the value of m1 and m2, that is, it will be minus minus plus del u del x by del u del y dot del v del x by del v del y, and from the Cauchy Riemann equation we can write del u del x equals to minus of del u del x equals to del v del y. So by using Cauchy Riemann equation, I am writing del u del x as del v del y, and then del u del y equals to minus of del v del x. So I get del v del y divided by del v del x into del v del x by del v del y with a negative. That means they all cancel with each other and we get the value of minus of 1. So that means the family of curves given by uxy equals to k1 and vxy equals to k2 are orthogonal to each other, thus prove the statement. Okay, so the third property is also proved. And again, I am asking for the comments or the feedback from your end. So after this, I will move to some problems of complex theorem or complex variable. Is it okay? Okay, so you don't have any queries till now? Okay, fine. Okay, so let's move on to problem number 1. The first problem is determine if and where the functions z, z prime and z square are analytic. So what is the problem? That is, the problem tells that determine if and where the functions z, z prime and z square are analytic. So here in this problem, we are asking about the condition, or rather we are asking for verifying that whether these two functions z, z prime and z square are analytic or not, and if they are analytic, if these functions are analytic, then we have to find out the region in which these functions are analytic. Okay, so let's solve this problem. So first of all, let the function be if z equals to z, z prime. Now, as we know that z means x plus jy and z prime means x minus jy, so it will be x square plus y square. Now, x square plus y square, it means that it is a real function, as because its imaginary parts are 0. So u of xy, as because u of xy is the real part of our complex variable, so u of xy is actually this real part, that is x square plus y square, whereas v of xy, as because here it is only a real function, so v of xy, that is the complex part of any complex variable, here in this case it is equals to 0. Now from Cauchy Riemann equation, del u del x, from Cauchy Riemann equation, del u del x equals to del v del y. So from this equation, if we find del u del x means twice of x, and del v del y, as because v of xy equals to 0, it will give us del v del y equals to 0. Now, the second Cauchy equation, that is del u del y equals to minus of del v del x, and here also del u del y gives us twice of y, whereas del v del x gives me 0. So from this function, using the Cauchy Riemann equation, I obtain these values of x and y, where x equals to 0 as well as y equals to 0. Now, as we know that x and y both are 0 in the origin, that is, according to satisfy the Cauchy Riemann equation, the value of x and y, both of them are 0, and this is true at the origin, but not in the neighborhood of the origin, as because as we all know that x, y equals to 0 is the coordinate of the origin. So from the Cauchy Riemann equation, or to satisfy z square z, z prime, that is the function z, z prime, to satisfy Cauchy Riemann equation, x and y both of them are equals to 0, and it can be true, or it will be true for only at the origin. But if we move on to the neighborhood of the origin, x and y cannot be equals to 0. So this function, that is z prime, is not analytic anywhere. So this function z prime is not analytic function anywhere. Now let's move on to the next function, that is z square. That is z square. So here the function is taken to be f of z equals to z square, that is x plus jy whole square. It means x square plus j square y square, that means minus of plus twice j xy. So here these two terms are the real terms, that means u of xy. U of xy is actually x square minus y square, and v of xy, that is the complex part or the imaginary part of the complex variable, is twice of xy. Again, from Cauchy Riemann equation, that is del u del x equals to del v del y. So let's find out del u del x from this. That is, it will give me twice of x, and then find out the value of del v del y. And here we are getting that del v del y is actually also equals to twice of x. Now the second Cauchy Riemann equation, that is del u del y equals to minus of del v del x, and if del u del y gives me minus of twice y, and del v del x is actually equals to minus of twice y. So here we see that these equations are satisfied at all points in the xy plane. So the function z square is analytic everywhere, as because this function satisfy Cauchy Riemann equation in all the points in the xy plane. So the function z square is analytic everywhere. Okay. Okay, or have you any doubt? Is it okay? Now let's move on to the second problem. Let's move on to the second problem, that is the real function uxy. The real function uxy, which is given as a plus the real function uxy, which is given as ax plus by, obviously satisfy Laplace's equation. The second problem states that the real function uxy equals to ax plus by obviously satisfy Laplace's equation. Hence find its complex harmonic function. Hence find its complex harmonic function and write f of z. Now the conjugate harmonic function. So the conjugate harmonic function denoted by vxy. I have already discussed about the conjugate harmonic function, and the conjugate harmonic function denoted by v of xy is related to u of xy by the Cauchy Riemann equation. Thus, del u del x here in the problem it is given uxy equals to ax plus by. Okay. Now the conjugate harmonic function vxy is related to u of xy by the Cauchy Riemann equation, that is del u del x equals to del v del y. Now del u del x means here a. So from this we get del v del y equals to a. Now we have to find out this function, that is the complex harmonic function, that is we have to find out the value of v. Okay. So now here if del v del y equals to a, we can find v as ay, that is integrating, we get v equals to ay plus a function of x. We obtain v equals to ay plus a function of x, and that is a constant gx, and yet it to be determined. So the relationship above must satisfy the other Cauchy equation, that is del v del x. That is the other Cauchy equation, that is del v del x equals to minus of del u del y. So from here, if del v del x, we are going to find out the value of del v del x, it will become minus del v del x means g of x. So del v del x means g prime x or dg dx. So we get dg dx equals to minus of del u del y, and from the main equation del u del y means only b. So this will be minus of b, or from here if we integrate this equation we get gx equals to minus of bx plus another constant c. So finally the value of vxy, that is the conjugate harmonic function of uxy, is actually ay plus gx, and then putting the value of gx, it will be ay minus bx plus constant c. So this is the conjugate harmonic function, or this is how we obtain or we find out the conjugate harmonic function of any harmonic function. Now in this problem we are also told, or we are also asked to find out the value of f of z. Now f of z means u of xy plus j v of xy. So this will make the value of uxy, and uxy as it is given in the problem, it is ax plus by, and then plus j v of xy is ay minus bx plus c. So f of z is a of a, as we take a constant, it will give jx plus jy. Then taking j constant, we have ay minus no, let's take j and b as constant. Okay, minus j and b. So taking minus j and b, we have x, then plus j y, as because j square means minus 1, and minus of j square, that is plus by, and this is the term plus by, and then the last term, that is jc. So this will be x plus jy into a minus of jb plus jc, and x plus jy means z, so it is a minus jb into z plus jc, or it can be written as k1 z plus k2, where k1 and k2 are complex constants. Is it okay? If you have any queries, please ask me right now, or otherwise I am going to end this class. So this is actually an introductory class of complex variable. I think after that you can proceed for the rest of your syllabus. Okay, so I'm ending this broadcast. Okay, goodbye.